Okay. Okay, recording is started. The live stream is taking some time.
Okay, sure. We can maybe wait 1 or 2
We can
minutes.
go ahead. We can go ahead.
Okay. Okay, sure. Good morning, everyone. I am Orignopan. Today's event is organized by Karilif, a math club of MTTS alumni in collaboration with MTTS Trust. It is my pleasure to welcome you all to the first session of the series of 2 invited talks being delivered by Professor V.G. Thomas. He is professor at the School of Mathematics at ISA Tiruvananthapuram. So welcome, sir.
Thank you. Let me try to share this slide.
Okay, so he will be talking about the maximal implies prime principle. Today's talk focuses on discussing several results that show an ideal maximal with respect to some properties happens to be prime. So
Yes.
before we begin the session, there are few essential guidelines for the audiences. So there you are always welcome to ask questions. However, before asking questions, please use the raise hand feature on Zoom and then unmute yourselves once you are invited. Also, once there are questions, and if you have the answer, please raise hand and unmute when you are asked. Otherwise, throughout the sessions, you are requested to keep yourself mute and keep the videos off so that no unwanted disturbance happens. Also, you can drop your questions in chat box or you may ask questions at the end of the talk. So, I have attended 2 courses at ISA TVM taught by him, and his lectures are incredibly engaging and presented in a clear and enjoyable manner. So, therefore, I am thrilled to invite you all to an enriching and delightful session. Over to you, sir.
Thank you. So, good morning, all. Let us start with the type of theorems or the results that I want to show you. So first, I'll write a bunch of results and we will see some common theme among them, and maybe we'll prove 2 or 3 of those results. So let me start with this one, though this is not the most element. It doesn't write what is. Yeah. Here. I chose this as the first one because it's by Marty Isaacs, who sadly passed away a couple of days, 2 or 3 days ago. So let R be a commutative ring with unit, with identity. Let I be an ideal. Let be a non-principal ideal. If I is maximal among non-principal ideals, then I is a prime ideal. Okay. So this is one type of result. So let me write a bunch of results so that you see that an ideal maximal with some property happens to be a prime ideal. So second one. So in the talk, the rings are always commutative rings with identity. So I will not state that every time. So let's write. So I will skip the first line for this theorem. R is always a commutative ring with identity. Let I the symbol for ideal is this now. Let I be an ideal that is not finitely generated. If I is maximal, I is maximal among non-finitely generated ideals, then I is a prime ideal. Okay, so as you see in these two results, I is maximal with some property and I happens to be a prime ideal. Now I will continue with this. We'll not right away prove. I want to show you there is a bunch of such results. And how do you go to the next page? Sorry, just a moment. We are
Just
trying
a
to add. There it is. I got
Yeah.
it. So this can be removed or what?
Maybe we can go and put it down.
Okay, can you put it down? Yeah. Thanks. Another one. Theorem. Let R be an integral domain. Okay. I will define some of these terms later. Let I be an ideal of R that is maximal among ideals that are non-invertible. Then I is a prime ideal. So as you see, the theme continues. I is maximal among ideals with some property, and then I happens to be prime. Let's continue theorem. Let I be an ideal of R that is maximal, ideal R that is maximal with respect to containing only zero divisors. Okay, so I is an ideal that is maximal with respect to containing only zero divisors. Then I happens to be prime. Now let's continue still. This is the more elementary and maybe many of you might have seen it. Let S be a multiplicatively closed set. S container be multiplicatively closed. If I, an ideal in R, is maximal among ideals with respect to disjointness. With S, then I is a prime. Let's continue. I mean, I want to state one more maybe, and then we can go ahead with perhaps proving one or two of this. Another theorem. Okay. Let R be a ring. This is by Herstein, I think. Let R be a ring and M be an harmonic. Let I be an ideal in R, maximal among all annihilators of non-zero elements of M. Then I is a prime ideal. So as you see, we have stated at least 5, 6 theorems. This is by Cohen. And each of these theorems will have a corollary which itself will give a nice result. And maybe we start with Isaac's and Cohen's theorem. I'll try to prove these theorems. And maybe then we can stop. And I will tell you what will come in the next lecture, which is of the same spirit. So let's start with Martin Isaac's theorem. So next. So, okay, I want to say again, look, all the results so far, what I wanted to say about maximal implies prime principle meant this, meaning you take an ideal and it is maximal with respect to some property, then I happens to be prime. The first two results here are of that type. All the rest are also of that type. I will define some of the words here if you are not aware. Disjointness with S, multiplicatively closed set. This all I will define. Zero divisors, I'm hoping that you know. So perhaps this you have not seen, I don't know. Let I is an ideal that is maximal with respect to containing only zero divisors, then I is a prime ideal. Yeah. So let's start with Martin Isaac's theorem. Okay. So theorem was, now I'll write in short. I is an ideal in R. I is maximal among non-principal ideals. Then I is prime. Then I is a prime ideal. Okay. Okay, good. So proof. So I is not a principal ideal, and it is maximal among ideals that are not principal. Then I happens to be a prime ideal. This is what we are claiming. So suppose not. Then suppose not meaning what? I am assuming I is suppose not prime, is not a prime ideal. Then there are elements A and B such that AB belongs to I, but A does not belong to I, B does not belong to I. So we have elements AB such that AB belongs to I, but A does not belong to I and B does not belong to I. Okay. because we are assuming that I is not a prime ideal. Yeah, I also don't know. Some sound is there. You can check. Here you have to check. We are just seeing what the sound is. There is a sound that keeps coming, but okay. Okay, yeah. Okay. I hope the handwriting is okay because I'm not used to writing on this, so it's not coming out well. But anyway, no. So now consider this ideal. Consider the ideal I, comma A. Now A does not belong to I, so IA is an ideal that strictly contains I. Correct? And look at the proof. All the proofs will go similar, and then at the end I will post some questions. So consider the ideal IA. A was not in A is assumed not to be in I, and so I is strictly contained in IA, and I is maximal among not principal ideals. So what can you say about IA? IA has to be, because I was maximal among ideals that are not principal, and you have produced an ideal that is bigger than I, so it has to be principal. So by maximality, of IA is principal. IA is a principal ideal. So since it's a principal ideal, let's say IA is generated by C. Huh? C is an element of our ring, of course. So we have this, okay? Good. Now, again, there is, so look at the proof, and the other theorem that we'll do will also go similarly. So that's why this is some kind of a principle we are saying that maximal implies prime principle. So now consider the ideal. We'll call J is defined as I colon A. This is called a colon ideal. And let me write the definition of this. It is the set of all, say X belongs to R such that X times A belongs to I. This is the definition. And it is easy to check. I'll leave this to you. It is easy to check that this is an ideal. Okay. So we have this. Let's go to the next page. I will repeat. J was IA. I'll repeat, that is equal to the set of all X belongs to R such that XA belongs to I. And we noted that this is an ideal. Now clearly you can see one thing. I is contained in J. Why is I contained in J? Because if I take an element of I times A will always belong to I. So I is clearly contained, right? Now, okay, so this is where now we want to say claim is that B also belongs to J. Okay, so I think this is not, it automatically happened. Let me see. I can read.
Someone did.
Oh,
Mistake.
by mistake. So I can't erase that. Okay, good. So let us look. So see what was, let me also recall from the last page. Let me recall from the last page. J, which is IA was also written as C because it was principal. No, not J. Sorry, let me, this I have to erase. Where is the eraser? Ah. So from last page, we wrote one thing. Then let me remind you. That is I, comma A was generated by a element C. Okay. Therefore, C can be written as what? Can somebody tell how can I write C? Particular C can be written as some I plus RA, where I belongs to I and R belongs to R. We can write this C as like this. Okay. Now let's multiply this by B. Okay. If I multiply this equation by B, what do I get? BC is equal to B times I plus R. It's commutative ring. So B times RA is R times AB. Okay. Now, what can you say about where does this BI belong to? I belongs to I. So BI belongs to I. Now, our hypothesis, the first line of previous page said AB belongs to I. First line of this said AB belongs to I. So this belongs to I. So RAB belongs to I. So in total, what we got is BC belongs to I. BC belongs to I means what? Oh, I want to keep this as C. Okay, this is XC. So I'm changing. Huh? What? Okay, so I have to make a change. Uh, uh, yeah, so I'm considering this ideal, J. Okay, IA was C, and I'm considering that, okay, here I wrote IA, but I'm changing it. What I want is IC. So previous line, I will consider this as C. Okay, XC, XC belongs to I. Okay, so next, this is XC, XC belongs to I. And from the previous page, IA was C, and now I'm considering this particular ideal J, which is I colon C. By definition, it is X belongs to R, such that XC belongs to C. Now, what have we seen? BC belongs to I. So what can you say about B? This implies B belongs to J. B belongs to J. Correct? So, pardon this error. The error was IA is C and the J I want to consider is colon with C. I colon C. This is a set of all X belongs to R such that X times C belongs to I. And I said, you check that J is an ideal. And I repeated, we are considering J the colon ideal with C, and it is that. And I is contained in J is clear. Why? Because any I, if you take, that multiplied by C is going to be in I anyway. So I is contained in. But we also showed that B is also contained in J. So that means what? I is strictly contained in J, which is IC. Why? Can somebody tell me why? Because we observed that I is clearly contained in J. We want to show that I has at least one more element more than I. And B was not in I. Since B is not in I, but B is in J, so we have shown that I is strictly contained in J. Okay. So what can you say now again?
That
I was
is
maximal with I is maximal with respect to some property. So J is principal. Good. So this means by maximality, J equal to IC is principal. Okay. before proceeding, let's go through the proof just once more to see, because I made that like typo here. So I don't want you to get lost. So let me quickly go through this again. Because this same proof works for mostly, the same principle works for all the statements I have stated. So it is good to just stop and go through the argument once again. So we are supposed to prove I is a prime ideal. We said suppose it is not a prime ideal. Then we can find elements A and B belong in R such that AB belongs to I, but A does not belong to I and B does not belong to I. Because prime ideal means what? What do you have to prove? If AB belongs to I, then either A belongs to I or B belongs to I. And we have assumed I is not a prime ideal. So because of that, we can do this. Now, A does not belong to I. So the ideal generated by I and A is strictly bigger than I. So by maximality, it is principal. And so say IA is principal and it is generated by C. Now we are considering the ideal called the colon ideal. This will keep repeating in other proofs also. Consider J, I colon C. That is the set of all elements in R such that when X is multiplied by C, you get in I. And you have to check that this is an ideal. It is an easy check. If you know what is the definition of an ideal, then this is an easy check. So you have that. Now the aim was to show that J is also strictly bigger than I. So all this calculation amounts to showing that J is strictly bigger than I. So let's see what the definition of J was. J was this. And IA was C. Now, I is clearly contained in J because any element of I multiplied by C will always in I. So I is clearly contained in J. I want to show that actually J is strictly bigger than I. Now, B is an element in I, but B is not an element in I. So first, because IA is C from the previous page, C can be written as I plus RA, where I belongs to I and R belongs to R. All we have to do is multiply this equation by B. This is BC is BI plus RAB. It is BRAB, but BRA, but it's a commutative ring, so I can write it as RAB. So BI belongs to I and AB belongs to I, so RAB belongs to I. So in short, BC belongs to I. When BC belongs to I, that means B belongs to J by definition of the ideal J. So now you have produced an element in J, but that was not in I. So J is strictly bigger than I. So by maximality, J is principal. Okay, good. So now the claim will be this. So I hope now we reviewed the proof because of the typo. Proof is I is C times J. Meaning it's C times J is what the claim is. Now, what can you say about this containment? This containment means C times J is contained in I. I want to say this. What can you say? Is it clear? Now, J is a principal ideal. Now, C times any element of J will land where? In I. So this is clear by definition. Okay. So that means we are supposed to prove only one more inequality, and that is this one. I is contained in Cj. Okay, this is what we want to prove. Now, I was contained in Ia, but Ia was C. We are remembering this. This is just reminder. I was strictly contained in Ia, and Ia was principally generated. So this we know. So now let's try to prove this inequality. Now, this is just a reminder. This is a reminder. So let I belongs to I. Right? So this means what? Since I belongs to I is contained in IA, which is strictly bigger, and that is I belongs to C. This implies I belongs to this C. Why? Because I is in I and I is contained strictly in C, so I belongs to C. Therefore, I equal to RC for some R belongs to R. Okay. Okay. Good. So now we are kind of done. Why? Why are we done? See what has happened. Can somebody tell me? What can you say about R? What has happened? RC belongs to I. See, RC is okay. Maybe I'll erase and I'll erase this line and tell you once again a little bit more. So what has happened? Implies RC equal to I, which belongs to I. If RC belongs to I means what? R belongs to what? Huh? What was J? J was, let's remind. Again, a reminder. J was defined as I colon C, which was as set of all X belongs to R such that XC belongs to I. And now we have RC belongs to I. RC is equal to I, which belongs. So this implies R belongs to J. Therefore, I, which is written as RC, which can also be written as CR, belongs to CJ because R belongs to J, right? Therefore, what have we proved? Therefore, I equal to CJ. J was principal, right? Why is J principal? Let's look at the previous page. By maximality, J is principal. Huh? So if by maximality J is principal, suppose it was principal and generated by D. So here what will happen? It is C times principal ideal generated by D. It is nothing but generated by CD. And so I is principal. What can you say now? What is the problem? I was a not principal ideal and it was maximal among non-principal ideals. So, but now we have produced that I is principal. So this is a contradiction. So what this is a contradiction because I is a non-principal ideal but we showed it is principal. This proves what? I is prime. Because we assumed I is not prime and we got a contradiction. So therefore, I is the prime ideal. Okay. So we have proved one of the results, and I chose this Martin Isaacs result first because, as I said, he is a very influential mathematician and just passed away about 2 or 3 days ago, and it's lost the community. I thought I'll start with this. Now, let's see. You may think, okay, if some ideal with some property happens to be prime, but so what? But it gives you a nice theorem. Now we'll see the theorem. Okay, so as a corollary, we can see a theorem. So plus. So as a corollary of this theorem of Martin Isaacs, we see another theorem, which is also, of course, Martin Isaacs. If R is a commutative ring, with identity, of course, so I'm not repeating. All my commutative rings are with identity such that all prime ideals are principal, then R is a principal ideal ring. Okay. So what is happening? No, I'm not saying principal ideal domain. This is what you might have heard. But principal ideal ring means what? Every ideal. It is not necessarily an integral domain. It is a commutative ring, but every ideal of the ring is principal. And the theorem is saying, if you want to check whether an ideal is principal ideal ring, all you have to check is whether all the prime ideals are principal. If you can check all prime ideals are principal, then every ideal is principal. That is what this says. This is also due to, this is the theorem due to Martin Isaacs. Oh, this is by my mistake. So I don't know how to remove that, but that was not meant. Martin Isaacs. Theorem is by Martin Isaacs. A very, very famous character theory representation theorist. Okay. So proof. Proof is very simple application of Zorn's lemma. Okay. So suppose not. Okay. When I say suppose not, what do I mean? Suppose R is not a principal ideal ring. Okay. That is what I'm assuming. When I say suppose not, so suppose R is not a principal ideal ring, then I can consider this set of all I such that I is an ideal of R that is not principal. What can you say about this set S? Is it empty or it's non-empty? Can somebody say it's an empty set or a non-empty set? See, suppose not means what? R is not a principal ideal ring. So there are ideals that are not principal. So S is not empty. So S is not empty. Okay. So therefore, by Zorn's lemma, you use Zorn's lemma to produce an ideal that is maximal among ideals that are not principal. So by Zorn's lemma, S has a maximal element. Say J. That means what? J is maximal among ideals that are not principal. What can you say from the previous result? Therefore, by previous result,
J is prime, right?
yes, previous result, J is a prime ideal. But what does the hypothesis say? All prime ideals are principal. Therefore, J is principal by hypothesis. But what is the problem? This is a contradiction. Yes. So J is not principal. So this is a contradiction. Therefore, what? R is a PIR, principal ideal ring. Okay. So you see, you proved a property of an ideal with some property, meaning some ideal which is maximal with respect to some property. And we proved it is a prime ideal. As a result, we were able to show that to check whether a ring is a principal ideal ring, then all you have to check is to see whether prime ideals are principal. So if all prime ideals are principal, then all the ideals are principal. So that was the moral of the story for this. Okay, good. Now, you may wonder, okay, maybe I should just say, maybe here as an example. Okay, see, PID, there are lots of PIDs. Can you tell me example of a principal ideal ring? I want to say, because you should not think that, oh, we have only seen PIDs. What is an example of maybe something like this. Huh? So what is this? Kx is a PID, right? K is a field, suppose. So Kx is a PID. Kx is a PID, and I'm saying this is a PIR. See, this is not a domain because X is an element such that when I multiply by X, it becomes 0. So this is not a domain. But so basically, quotients of principal ideal domains happen to be PIDs. In fact, there is a, maybe this is not part of the lecture, but since we came here, maybe I'll write just as I say, it's an old theorem of Hungerford.
Actually, even Z mod NZ.
Yes. So there are several. Yeah. So basically, let me write a theorem of Hungerford. I'll not write very carefully. So if R is a principal ideal ring, then R has to be product of products of quotients of PID, basically. So R will be, say, product of quotients of PIDs. Okay. Product of quotients of PIDs. So this is PID, and this is a quotient, and it will be products of such. And this is a theorem of Hungerford, old theorem of Hungerford. Anyway, this was not the purpose of mine. It just somehow I went in a tangential way. So yeah, so this is not was the purpose. But I hope I made it clear that how assuming something ended up assuming an ideal maximal with some property happens to be prime. Yeah. So let us go one more. What is the time? Yeah, I have about at least 15-20 minutes. Maybe I'll get one more theorem done, and maybe then plus. Okay, let's go one more. This is a very well-known theorem by. The reason I want to prove this and show this is because this is what we will generalize in the next lecture. I want to generalize this and as an application show Ekin-Nagata theorem and theorem of Jyotirlinga. I.S. Cohen. Suppose I is an ideal in R. This notation is for ideal. And assume I is not finitely generated. You will see the proof goes exactly same as we did. And assume I is, and then at the end, I will pose a question. Not finitely generated. If I is maximal among ideals that are not finitely generated, then I is prime. Okay. Again, the proof follows the same way. And so that's why at the end, I will pose a question because all of this result goes the same way. Suppose not. Then like previous time, what can you say? Then there are elements A and B in R such that AB belongs to I, A does not belong to I, B does not belong to I. Huh? Again, what was the next line in that theorem? Take I, comma A. A does not belong to I. So I, comma A strictly contains I. So what can you say? That ideal is finitely generated. So that's exactly how it will go. So note that I is strictly contained in IA. Because A does not belong to I. I is of course contained in IA. And A does not belong to I. So this is strictly bigger. So by maximality, IA is finitely generated. Okay. So therefore, we can write it is finitely generated. So we can write is generated, say, by I1 plus R1A dot 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 IN plus RNA. Okay. And let's name this star. We'll use this. Why did I put it I1 plus R1A like that? Because the elements of IA are of this type. So, and it is finitely generated. We have obtained because of maximality. So it is finitely generated by this elements is all we are writing. This is a comma. If you don't, it was confusing. This is comma and this is dot dot dot. There are n such elements. Now again, like previous time, what should we do? Consider colon ideal. Now, so here consider J I colon A. Okay, we'll consider this ideal. Now, like previous time, what can you say? I is clearly contained in J. Why? Because any element of I multiplied by A will go into I. So clearly, I is contained in J because why? Take an element X in I, X times A, X is in I, so any element of the ring multiplied by that X has to be in I. So X, the I is clearly contained in J. We want to show that is bigger, strictly bigger than, like last time. So how do we show it is bigger than I? What is the element that I should choose? Note that B belongs to J. Why does B belong to J? Because B belongs to J because AB belongs to I. AB is equal to BA. BA equal to AB belongs to I. And B times A belongs to I means what? B belongs to J. But B was not an element of I. So therefore, conclusion is I is strictly contained in J, which is the colon ideal IA. So by just like last time, what should you say? By maximality, what can we say?
J is finitely generated.
Generated, exactly. Therefore, by maximality, J is finitely generated. Okay. So let's continue. Since J is finitely generated, J was denoted by this. J was precisely this colon ideal, and it was finitely generated. Let's say it is generated by S1 dot 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 ST. Okay. Now the claim. Claim will be as follows. I will be generated by I1 dot 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 IN comma S1 dot 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 ST. Okay, let's go back. What is I1 to IN? So in previous, see, IA was generated by I1 plus R1A, I2 plus R2A dot 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 IN plus RNA. So in the next line, the I1s I'm choosing are these I1s. So next. So those are the I1 to IN, and S1 is just this one. But not, I want to modify. Let me take the eraser. It's not this one. I have to modify a little. Okay. So this was a comma. This is a comma. This is a comma here. S1A, I want to do dot 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 STA. Okay. This is what I want to write. Good. Now let's see. This side again is going to be trivial like previous time. I1 to IN, Where were they? Where did I1 to In belong? Let's go and look at the previous page. Here I should write what? Here Ij or Ik belongs to I. That means I1 to In belongs to I, and Ri, Rk belongs to R. Okay. So the Ri's are in R and Iks are in I. So all these are in I. Okay. Now, so I1 to In all are in I. I want to show this direction. Now, what about S1a? S1 belongs to J. That means S1a belongs to where? Can somebody tell me? See, S1 to S1 belongs to J, so S1a belongs to I. S2 belongs to J, so S2a belongs to I. ST belongs to J, so STA belongs to I. So I1 to IN belongs to I, and S1a to STA also belongs to I. So this containment is clear. So therefore, I1 IN S1a STA all belong to is contained in I. So this is clear. Clear. This we explained and it's clear. Each element is in I. Now we have to go this way. Last time also this direction needed little bit proof. Here also it will be same. So how do we do this? Last time how did we first notice? Recall from the proof earlier, from the previous page, recall that I was strictly contained in IA, correct? It was strictly contained in it. So we will recall this. Now I want to show this containment, meaning I is contained in this ideal generated by all these elements. So let X belongs to I. So X belongs to I means what? X belongs to IA. And IA was finitely generated. Look, previous page. IA was finitely generated by these elements. So let's write. Therefore, by star, let me show you star, previous page. Star means IA. See, X we chose in I, and I is strictly contained in here, and all these elements are generated by those elements. So by star, X can be written as X equal to what? Lambda 1 I1 plus R1a plus lambda 2 I2 plus R2a plus plus lambda n IN plus RNA. Okay, good. So this can be rewritten as, let's expand. I mean, it's easy. I can not expand and still explain, but it's better to once expand and see what happens. I'm putting all the lambda and INs together. This is 1 plus what? Lambda 1 R1 plus plus lambda n Rn and A. Okay, that is X. Now, let's look at one thing. Where was X? To make sure that you are following, and at the moment we are not lost because the proof has continued for some time, but I'm hoping that I want to make sure that you are not lost in notations. And okay, where does X belong? Yeah, it is written here. X belongs to I. Where the I1s, II belong is in I. So lambda 1 I1 belongs to I. Lambda 2 I2 belongs to I. Lambda n IN belongs to I. Therefore, what can I write? Lambda 1 R1 plus plus lambda n Rn times A is equal to X minus lambda 1 I1 plus dot 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 plus lambda n IN. This belongs to I, right? Because X belongs to I and all these elements are in I. Now, if this belongs to I, let's call this double star. Okay, this equation I want to call double star. This one, the second one. Yeah. Now, if this belongs to I, what can you say? Therefore, lambda 1 R1 plus dot 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 plus lambda n Rn belongs to J. But J is finitely generated by those one. Therefore, lambda 1 R1 plus dot 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 lambda n Rn is equal to what? Alpha 1 S1 plus dot 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 alpha T ST, where alpha I belongs to R. Correct? Okay, good. So, what happens to double star? Let's replace this lambda 1 R1 whole thing by this in this double star. So let's call this maybe triple star. So using triple star in double star, so by star star and star star star, what do we get? X equal to lambda 1 I1. Oh, sorry, this is I1 plus, sorry, on I1 plus dot 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 plus lambda n IN. This is one bracket as it is. And here we will replace this by plus alpha 1 S1A, right? Plus dot 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 plus alpha T STA, right? So what have we proved? Therefore, X belongs to this I1 dot 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 IN comma S1A dot 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 STA, right? So what has happened? Oh, sorry, not previous, next. And plus, therefore, I is contained in this ideal, I1, I2, dot, 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 IN, then S1A, dot, 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 STA. So in upshot was, we showed what we set out to do, which is I equal to this ideal. Right? So this means what? I is finitely generated, and that is contradiction. So therefore, I is a prime ideal. Let me write the corollary of this theorem. Again, a theorem which is a corollary of this theorem. What is the corollary? Can somebody tell? Again, the same statement like previous. Taking hint from the previous corollary, can one of you state what the... See, that happened that if prime ideal satisfied some property, then every ideal satisfied that property. So it has to be some such theorem. Okay. So let R be a commutative ring. If, okay, this I have to erase. If every ideal, if, sorry. Just like last, everything exactly it is following the same. If every prime ideal of R is finitely generated, then every ideal is finitely generated. And every ideal is finitely generated is something called Noetherian ring. Huh? That is, R is a Noetherian ring. So Noetherian ring, there are various definitions, but the simplest one, every ideal of the ring is finitely generated. So to show that every ideal or is finitely generated, which is saying same thing as saying that to proving R is a Noetherian ring, it is enough to show every prime ideal is finitely generated. Okay, good. Now tomorrow, so this is also theorem of I.S. Cohen. Tomorrow, I want to give a generalization of this theorem. And that theorem will be a theorem of, so tomorrow, we will generalize Cohen's theorem. And also obtain another theorem as a corollary, which is called the Ikin-Nagata. Okay, so that is the aim for tomorrow. Now, let me now leave as exercise for you guys say this is easy one that I think you should all get it. Even this you should try. Next, let's try this too. Okay, see the way we have proceeded. If you proceed, what should be the can at least let me see if you have understood the principle. What should be the corollary of this theorem? See, we have proved two theorems and we had corollaries which allowed us to check whether if every ideal has some property, it was enough to check whether the prime ideals have that property. So here, what should be that kind of a theorem? Let R be an integral domain. The theorem consequence of this theorem will be let R be an integral domain. If every prime ideal is invertible, then every ideal is invertible. Okay. And this kind of, there are rings called Dedekind domains in which every ideal will be invertible.
So what does invertible ideal mean?
What? Invertible. Invertible
Invertible
means,
ideal.
what was the question?
I mean, what does invertible ideal mean? Yeah. What does the term invertible?
Invertible ideal. I couldn't hear. So let me write the definition. So next. Okay, here we can write, invertible. So I will only define when it is mostly common to define that. R in this case happens to be domain. So an I is an ideal, suppose. I can introduce fractional ideal, but let's not at the moment do this. So I inverse is a set of all R, and field of fractions of R is suppose K. If you don't know field of fractions, it is same process of obtaining Q from Z. invert every non-zero element and make it the field, and that's the way you make a domain a field, and this is the process. So I inverse is a set of all elements of K such that X times I R. Now, a fact or easy thing to check is that I times I inverse is always contained in R by definition. Okay, this is always. If I times I inverse equal to R, then I is called invertible. With inverse, I inverse. Okay, so that is what invertible ideals are. So, in fact, invertibility, when it is a domain, invertibility is same as if you know what is a projective ideal. So I is invertible, then I is projective as a R module. So you can prove this, but anyway, these are additional terms. At the moment, we don't want to do it. But invertible definition is this. Yeah, so with this definition, you can prove that theorem. Or if you don't want to go with that invertible one, why not go with this one? This has all words that are not so difficult here. I is an ideal that is maximal with respect to containing only zero divisors. Then I is a prime ideal. And can you state what could be the kind of, what could be the theorem as a, that comes out as a corollary for this? Can somebody tell me? This is maybe slightly, this is not very common. I mean, this is not a very common. You perhaps many of you may not have seen it. Some maybe have seen it, but not many might have seen it.
I think it will begin like if all prime ideals of R contain only zero divisors.
No, so yeah, so it's in the similar style, but the way it should go, if all non-zero prime ideals are regular meaning an ideal is regular if it contains at least if it contains a non-zero divisor. Okay, if all non-zero prime ideals are regular, then the ring is an integral domain. That is the corollary of this theorem. See, the theorem that appears as a corollary of the maximal implies prime is almost negation of the original one that we did. See, if all prime ideals are finitely generated, then all ideals are finitely generated. But it appeared as a corollary of if all ideals that are maximal among non-finitely generated ideals, then it happened to be prime. And its non-finitely generates opposite is kind of finitely generated, and that principle. Here it says containing only zero divisors. So the kind of opposite of is if all non-zero prime ideals are regular, meaning if it contains is a zero, at least contains one non-zero divisors, then R is a integral domain. So to check, you now know a new way to check integral domain. You have to check that every prime ideal has at least one non-zero divisor, meaning it's a regular ideal. Then it is an integral domain. So see, you can get such kind of theorems. So I hope I have conveyed what was the message of the talk is ideals that are maximal with respect to some property happen to be prime ideals. And as a consequence, you get a very good characterization of rings in the sense that the rings, if the prime ideals have some property, then all ideals happen to have that property. This is a kind of message that comes out of this kind of principle. And maybe I should say, at least people who knew this, we should feel little bad because I knew many of these results before, but I could not, I mean, I thought there was, but never sat down to really think, and there is a paper in 2008. I don't remember the title exactly. I will come with the title next time. Theorem of Algebra. I think it's T.Y. Lamb and M. Rias. I think it goes like the prime ideal principle or some such thing is the title of the paper. And they show that, see, all of these theorems that were proved by different times have a theme in common, and it is worth reading, going through the proof. And the reason I did this before is, one thing is, you now know that if you encounter a situation where you are in a situation where you have an ideal maximal with respect to some property, then it is not too bad to hope that it may be prime. Of course, you need to prove it, but that is a good hope to have. So this is it's a principle that you can keep in mind. And this is a paper, I think it is called prime ideal principle or some such thing. I forget now. Okay. And I presented this because tomorrow when we do this, the proof goes similarly. At that time, tomorrow, I will need for you to know what is a module and what is Noetherian. I mean, yeah. What is the notion of Noetherian ring, and that's about it, I think. Yes. So, and this is a very nice theorem. You can think about it. It says that you have two rings. A is contained in B. So A and B are rings. B is a finitely generated A module. Now the theorem statement, so these are the hypotheses. If B is a Noetherian ring, then A is a Noetherian. So this is a very beautiful, it's not obvious. So sub rings of Noetherian need not be Noetherian. You have some condition. Okay. So I think this is where I will end the talk. If you have questions, you can ask yeah.
Yeah, so if anyone have any questions, can you please raise your hand or just unmute yourself and can ask the questions? Anyone?
In fact, you should now try to discover, is there any other than the ones I stated? Can you discover any other ideal maximal with respect to this property now is prime? Then that is your new result, right? I mean, you can come up with a property and say I maximal. So there are other things like I didn't mention, I maximal among ideals that are not countably generated. We had said not finitely generated, not countably generated, that also will happen to be prime. And such, but there are many others which one can discover. I mean, it's waiting to be discovered, but one has to discover it, yes. So is
Are
there
there any questions?
Yeah, if
Yeah.
no,
Okay,
Sir?
so if no, is there any?
Hello?
Okay, so let's thank
Ones are
everyone
we
who have
supposed
joined
to
us.
Okay, sorry.
I think someone is asking something.
Yes, so which ones are we supposed to try? The one with zero divisors? The
try
one
with
that
zero
containing
divisors.
Zero divisors. Another is that disjointness with S. with
Disjointness with S is very easy.
Okay.
This is a
And
way
the
of
invertible one, right?
and
And the invertible one.
the invertible one.
Okay.
So this two you can try. The disjointness is very easy. You should all try to do it. Why the advantage? Let me say one advantage of this. This is a way of kind of coming up with prime ideals in a ring. See, What is a multiplicatively closed set? So S, a subset of a ring, is multiplicatively closed if one belongs to the identity belongs to the subset, and if A and B belongs to S, then AB belongs to S. Huh? If that happens, then this is multiplicatively closed. So if you can find one ideal that is disjoint with a multiplicatively closed set, by Zorn's lemma, you can expand that ideal to maximal with respect to disjointness with S, and the result says that it is then a prime ideal. So this way you can produce prime. But this is very easy to prove, and I'll leave this up to you. Then these two theorems you should try. And these two theorems you should try. And this usually will be covered in any commutative algebra course. This usually happens to be. So this will come up anyway. But perhaps this doesn't come up. This doesn't come up that often. This doesn't come up. So you can try this.
Hello,
Yes.
sir. Are there properties that somehow, if we know it hold for the maximal ideals, can we conclude it for every ideal?
No. That this doesn't happen. Yeah. So that is not. I mean, there may be some, but not like this. Not like the. So one can give even so this Cohen's theorem with finitely generated. If you want to try with maximal ideal, this will not work. So this is a specific prime ideal type of a principle. So the Cohen's theorem that we proved, if you try for maximal, you can produce counterexamples.
Okay. Are there any more questions? Anyone have any? Okay, so if there is no more questions, let us thank Professor V.G. Thomas for today's session. A link of feedback form has been shared in chat. Please spare a few minutes to fill out the form after the session and before 10 p.m. tonight. And now, if possible, I request everyone to turn on your camera and so that we can get group photo for today.
You can come here then. You guys can come here in case.
Yeah, sir, can you stop sharing the screen? Yeah, so
Oh.
that we can capture the photo. Yeah.
Okay. I have to stop sharing. I have to figure out how to show. Do you know how to stop this? I don't know how to. Try help me. Yeah.
Yeah, we
Hello.
can do one thing.
He will
Yeah.
help. No problem. Maybe just close it, I guess. Stop share. Here. Is it? It's gone,
Yeah.
right? Okay.
Yeah,
Yes.
right. Thank you.
Oh, I see many people who I kind of know. That's very good. I see Amit. I see. Shamik was also there. I see.
Hello, sir.
Hi, Vijay.
How are you?
Nice to see you. Very nice talk here.
Thanks. You are in Bombay, right?
No, I'm in Calcutta in this Vivekanand University.
Oh, great.
Okay, so shall we click a picture now?
Yes.
Okay. So on the countdown of 3, we will have a photo. So 3, 2, 1, smile. Okay, thank you, everyone.
Thank you.
Before we end today's session, so I want to remind you that the second lecture is tomorrow at 3 p.m. Please join us and have a good day. Thanks.
Bye.
Bye, sir.